An easy numerical scheme for integration is called trapezoid approximation. In trapezoid approximation, we approximate this region with this trapezoid. It's the trapezoid formed by the corner A, f of A, and B, f of B, along with the values A and B along the horizontal axes. Clearly, the area of this trapezoid is the average value of the height, f of B plus f of A divided by 2, times the width, B minus A. That's summarized in this expression. The trapezoidal integral is defined to be B minus A over 2 times f of B plus f of A. It's obvious that for most functions, this is not the exact value of the integral, but it's called the trapezoidal approximation to the integral. So clearly, the trapezoid formula is not the exact integral in general, but how accurate is it? Well, without additional assumptions on f, there's no manner in which to judge the accuracy. If the value of f at intermediate points between a and b has nothing to do with the values at a and b, then clearly the error in this trapezoidal approximation can be very large. However, if we make additional assumptions about f, then some quantitative conclusions can be reached, and that's what this theorem states. The theorem says, suppose the second derivative of f is bounded by a constant, I'll call m2, in the interval ab. In other words, f double prime of x is less than or equal to m2 for all x in the interval a to b. Then the error between the actual integral and the trapezoidal approximation is bounded by m2 times b minus a cubed over 12. We won't bother doing the proof of this. It's just a simple calculus argument, but let me show you one way to interpret it. Let's consider a quadratic function that has f of a equal to f of b equal to 0, but in between a and b, f is positive. For instance, let's take a equal -1, b equals 1, and f equals 1 minus x squared. There's a graph of it. At -1, the value of the function is 0. At +1, the value of the function is 0. But in between, the function is positive. The trapezoidal approximation will clearly give 0 because f of a is 0 and f of b is 0. So the trapezoid connecting those points is just the trapezoid of 0 height. On the other hand, the actual integral of 1 minus x squared from -1 to 1 is 4/3. Let's look at f carefully and see what the bound would tell us. Well, f double prime is just -2. Take the second derivative of 1 minus x squared and you get -2. Therefore, a suitable bound on the second derivative over the interval -1 to 1 is the number 2. That's a legitimate bound on the second derivative. In fact, it's the best bound on the second derivative. Now let's plug that into the formula we have for the upper bound on the error. Well, m2 times b minus a cubed over 12. m2 is 2. b minus a itself is 2. 2 cubed divided by 12. And lo and behold, I get 16/12, which is 4/3, which is precisely the actual error in this case. That's really the way to think about how trapezoidal integration makes errors. The trapezoid formula represents the area of a trapezoid connecting the 2 points a, f of a with b, f of b, whereas parabolas, which have non-zero second derivatives, deviate from that and have additional area that's unaccounted for in the trapezoid formula. This theorem is more general than just quadratics. It shows that the bound on the second derivative of f is enough to bound the error in the trapezoidal approximation. Now, how can the trapezoid formula be made more accurate? Let's look at something called the two-subdivision composite trapezoid formula. So here we have the graph of f and the area that we're trying to estimate. What we'll do is we'll apply the trapezoid approximation to two subdivisions of AB. Here I show the interval AB divided in 2. H is half the distance from B to A, and therefore A plus H is the midpoint. Now we can calculate the area of those two trapezoids and add them together. That should usually be a better approximation to the integral. So the definition of the two-subdivision trapezoid formula involves the area of the first trapezoid plus the area of the second trapezoid. Notice that the first trapezoid involves the value of the function at the midpoint, and the second trapezoid involves the function at the midpoint. So when we collect terms, we get an expression like this. F of A plus 2 times f at the midpoint plus f of b, the whole thing times h over 2. And that is what we'll call the two-subdivision trapezoid formula. Let's go over how accurate this should be. Well, there's an error bound in each subdivision, which is m2 times h cubed over 12. That's from the previous page. That's how much error we potentially make in the first trapezoidal integration from a to a plus h, and that's also how much error we might make in the second one from a plus h to b. Since there's two subdivisions the integrals add, the integral of f from a to b is the integral of f from a to a plus h plus the integral of f from a plus h to b. Therefore, the errors must add as well, and the error hence is at most 2 times the errors that we make individually. Plugging in what h is, remember h is b minus a over 2, we get b minus a cubed over 2 cubed. One of the 2's cancels, leaving a 2 squared in the denominator, resulting in a guaranteed error bound on the two-subdivision composite trapezoid formula. Hopefully this is all straightforward. Take the short quiz to see if your understanding of the trapezoid formula is complete.